Did you know that the simple act of water flowing downhill is actually one of the most powerful and, get this, most efficient ways to generate electricity on the entire planet? Well, today, we're going to follow that incredible journey, all the way from a single raindrop to the light that fills your home.
We are diving deep into the science of hydropower. It's a renewable technology that is just stunningly effective. It converts the energy of flowing water into electricity with an incredible efficiency of around 90%. To put that in perspective, that's higher than pretty much any other power source out there by a long shot.
So that's the big question, right? How do we take the simple, raw power of a river and transform it into something that can light up an entire city? That is the amazing feat of engineering and physics that we're going to unpack right now. All right, so here's our game plan. We're going to trace this whole journey of energy, step by step. We'll start with how we capture a river's power, then look at how we store that power up. After that, we'll see how it's unleashed through these modern water wheels called turbines, how that motion creates an electric spark, and finally, we'll check out the different kinds of hydropower plants and what the future really holds for this technology. First up, let's look at the basic building blocks. Because, a hydropower facility isn't just a big wall of concrete. No, it's a really sophisticated system of interconnected parts, and each one has a very specific job to do. Okay, so it all starts with the massive dam, which creates a huge reservoir behind it. Think of it as a giant battery made of water. Then you've got the intake, which acts like a gatekeeper, carefully controlling the flow and filtering out any junk. From there, water gets funneled into the penstock, this huge pipe that builds up a ton of pressure. That high-pressure water then blasts the turbine, making it spin like crazy. The turbine's connected to the generator. That's where the magic happens and electricity is born. And finally, transmission lines send that power out to all of us. It's really just an elegant and incredibly powerful process, all run by gravity. The whole process really kicks off by creating what is, for all intents and purposes, a giant water-powered battery. By holding all that water up high, we're storing a massive amount of potential energy, just waiting to be released. And the science behind that is a really fundamental principle of physics, potential energy. It's simple, really. Think of holding a bowling ball at the top of a staircase. The higher you lift it, the more potential energy it has, right? Well, a dam is doing the same thing, just on a massive scale, holding water at a much higher elevation than the river downstream. The more water and the higher it is, the more energy we've got on tap. And to figure out just how much power we can squeeze out of this, it all boils down to two key things. The first is called head. That's just the vertical distance the water falls. The second is flow, which is how much water is moving through the system. And the formula is super simple, but the results are astounding. The more head and the more flow you have, the more clean, renewable power you can generate. So when you look at it, the dam's entire job is engineered to maximize this potential energy in three ways. First, it stores a massive volume of water. Second, it creates that super important height or head, which gives the water its power. And third, it gives us precise control over the flow, so we can unleash that stored energy exactly when we need it most. All right, let's head into the heart of the powerhouse and see how all that stored up potential energy finally gets turned into motion. This is where the modern descendant of the ancient water wheel comes into play, the turbine. Now, turbines generally fall into two main camps based on how they use the water's force. You've got impulse turbines, which work kind of like a superpowered pinwheel. High-speed jets of water literally blast a series of buckets, forcing them to spin. Then you have reaction turbines. These are completely submerged, and they use specially shaped blades, a lot like an airplane wing. As water flows over them, it creates a pressure difference that generates lift, causing the whole thing to rotate. It's a bit more subtle, but just as powerful. Now, this is where it gets really interesting, because engineers have to pick the perfect turbine to match the specific site. For places with a really high head, like in the mountains, they'll use a Pelton turbine. For a low head, but a really high flow, like a wide, slow river, a Kaplan turbine is the way to go. And for pretty much everything in between, the incredibly versatile Francis turbine is the most common choice in the world. It's a perfect example of engineering being tailored to the environment to get every last drop of efficiency. So, the turbine has done its job. It successfully converted the water's moving energy into rotational mechanical energy. The turbine is spinning, and now it's time for the final bit of magic, creating electricity. And this whole process is only possible thanks to a couple of game-changing discoveries way back in the 19th century. In 1820, a guy named Ørsted found that electricity could create magnetism. But it was Michael Faraday who, 11 years later, asked the revolutionary question, wait a minute, if electricity can make a magnet move, can a moving magnet make electricity? And the answer, of course, was a resounding yes. And that beautifully illustrates what's called Faraday's law of induction. This one principle that a changing magnetic field will get electrons moving in a nearby wire is the scientific bedrock that our entire electrical world is built on. So here's how it works inside that generator. The turbine shaft spins the rotor, which is basically a bunch of giant spinning electromagnets. This rotor spins inside the stator, which is a stationary ring packed with tightly wound copper coils. As those powerful magnetic fields sweep past all that copper wire, they literally push the electrons along, creating a current. And that's it. We have electricity ready to go. Okay, so now that we've got the basic recipe down from potential energy to kinetic to mechanical to electrical, let's look at the different ways hydropower plants are actually designed to get this done.
First, you've got the one we all picture, the massive, absolutely awe-inspiring conventional dam and reservoir system. These are monumental projects designed to store just colossal amounts of water, and that gives them the flexibility to generate huge amounts of power exactly when it's needed most. Plus, they're not just power plants, they're also super important for things like flood control. Next, there's a totally different approach, run-of-river plants. These are much less disruptive, a more eco-friendly option. Instead of a giant reservoir, they just divert part of the river's natural flow through turbines. They generate a consistent, steady supply of power, but with a much smaller environmental footprint. The trade-off, though, is they can't store energy, and they're completely at the mercy of the river's seasonal flow.
And then there's pumped storage, which is an incredibly clever and increasingly vital system. It's not just about generating power, it's about storing it on a massive scale for the entire grid. It's like a giant rechargeable water battery. It basically operates in two modes. When there's extra, cheap electricity on the grid, say in the middle of a windy night, it uses that power to pump water from a low reservoir up to a high one, basically charging the battery. Then, during peak hours when power is expensive, it releases that water back down through the turbines, generating electricity really fast. This makes it the perfect partner for renewables like solar and wind that aren't always on. So, after this whole journey from a reservoir to a light bulb, what's the big takeaway? What does all this mean for our energy future? Hydropower isn't just powerful and incredibly efficient, it's also built to last. I mean, many of these facilities operate for over a century. That makes them a durable, long-term cornerstone for a stable and clean energy grid. As we move more and more towards renewables, the reliability and longevity of hydropower is going to be more important than ever. But this incredible technology leaves us with one final, crucial question for the future. As our demand for clean energy just keeps growing, we have to constantly ask ourselves, how are we going to balance the immense power we can get from water with our responsibility to preserve the vital river ecosystems that sustain our planet?